Alrighty, welcome back. And today we're going to be looking at solving a couple of trig equations. Now, these aren't examples found in the textbook. So if at the start of each example you want to pause and you want to do it yourself and then kind of compare it to my answer, feel free to do that. It's probably really good for your own understanding. But first of all, let's figure out what we're doing when we're solving trig equations. So just to give a rough outline of what's happening, solving trig equations is effectively finding the angles that satisfy the equation. So solving trig equations is finding all the angles. Now we'll add a little note here. In the given range, and we'll underline that because that's important, that satisfy the equation. Okay, now this is important because the unit circle causes particularly, well, all three trig ratios, but sine, cosine, and tangent to repeat. Okay, there may be many solutions. Okay, now, just a little note. Most of the time, not all of the time, but most of the time, we play on easy mode and you will always use exact value triangles. Or the general solution. Okay, because some of the values that you get might be a little bit gross, and so you either always use an exact value triangle, particularly when we're asking you to find like within a range, or you use the general solution. Okay. All right, so let's do a couple of examples. This is example 1. Solve negative cos of theta equals root 3 over 2 for all the angles, this should be, sorry, a theta, for theta in between negative 2 pi and positive 2 pi. Okay, so that means that we need to figure out all the angles that this gives us a cosine value of root 3 on 2, to make it negative, of course, and it needs to be within one full rotation positively or one full rotation negatively. So, firstly, we just look at this equation. Let's not freak out too quickly. We'll look at this equation. We'll just try to solve it normally. So we'll say negative cos of theta is equal to root 3 on 2. Okay, now we just need to get the trig ratio by itself. So we move the negative to the other side. Negative root 3 on 2. Okay, so because it's negative, this tells us the angle must be in quadrant. Well, what quadrant is cosine negative in? It's negative here, and it's negative here. So it must be in quadrant 2 or 3. Okay, which means we're not taking any angles which are in the first and the fourth quadrant, because we need cosine to be negative. So now we recognize that we don't care about the negative, basically. We just need to figure out what angle actually gives us a cos value of root 3 on 2, and then we'll just make sure that we end up in the right location for it. So in order to do this, we'll draw an exact value triangle. Again, this is what we mean when we say we play the game on easy mode. Usually it's always going to be one of these, otherwise you're just using the general solution. Root 3, 2, and 1, which means that our angle, sometimes called like our fundamental angle, is, well, which one gives us a cos of root 3 on 2? It's this one, pi on 6. Okay, but we can't just take cos, we can't just say pi on 6, because cosine of pi on 6 is positive root 3 on 2. So we need to make sure that we're ending up in the right quadrants. So we can say our solutions are... Now, actually, let me just give myself more space so we don't feel too cramped. Solutions. So then we just need to figure out, and this is why your textbook kind of sometimes just goes straight to the general solution, but I like doing this because it helps us visualize the unit circle. We can't go here, okay? Because that would give us a positive cosine. So that's a no, okay? Just erase that. But we can use symmetry to get to the other side, right? Like we could go here, or we could go here, okay? So for our positive solutions, that is if we're working like in this direction, those solutions are, well, what gives us a symmetry of the same cosine value but negative? It's going to be 5 pi on 6 and 7 pi on 6. That gives us a cos value of root 3 on 2, but it's going to be negative because it's in the other quadrant. And then we want also to negative 2 pi, which means we're just going to go in this direction, okay? Which is going to be negative 5 pi on 6 and negative 7 pi on 6. And is this all the ones within the range? Yep. So that's all of the solutions. Great. Okay. Let's move on. Example number 2. Solve 3 tan of 2 theta equals negative 3 root 3. Okay, so let's not freak out too much about the negative just yet. Let's actually just work kind of normally. So let me just move this unit circle up a bit so that way we don't get into any pickles, and I'll make a bit more space here. We are also going to make a little bit of a note of what your book says, because your book says something quite interesting and kind of want to show you why it's helpful but not necessary. So we're just going to solve it like normal, right? What color did I use? I used pink. Just solve it algebraically. 3 tan 2 theta is equal to negative 3 root 3. So we divide by 3. Tan of 2 theta is equal to negative root 3. Cool. Okay, so now at this point in time, we figure out, okay, well, what... We just do the same thing. So we say, we draw our unit circle, but not our unit circle, our exact value triangle, and we're trying to figure out what angle gives us a tan value of negative root 3. Well, actually, let's draw this down here. We'll keep it consistent. We'll draw it like this. Again, root 3, 2, 1, pi on 6, pi on 3. Okay, and before we even start to look at that, we also need to check what quadrants we're working in, right? We're saying that this is negative, or the tan value is negative. Negative. So the angle must be in quadrant. Well, where is tan going to be negative? It's going to be negative in this one and this one, right? So 2 and 4. Cool. All right. So we draw our exact value triangle as we've done, and we can say our fundamental angle that is the one that we're going to use, but we're going to transform depending on how we need it, is, well, which one gives me a tan value of root 3 over, well, of root 3? It's going to be this one, pi on 3. Okay. Great. And so now we're looking for all of the angles that give us the tan value being root 3 but negative. So we're in quadrants 2 and 4. So our solutions again, so this is, we can't do this. Okay, we can't say pi on 3 because tan would be positive here. But we can do it on the other side according to symmetry. We can do it over here, right, where this is pi on 3. Okay, so, but what angle would that actually be? That angle would actually be 2 pi on 3. So we can see our solutions are, our solutions are 2 pi on 3. And then we can also do the one down here, yeah, where this is pi on 3. Which means that it's also going to be, well, how many lots of pi on 3? That's 5 pi on 3. And then because we want to go up to 2 pi, that's it, right? Except that we haven't solved the equation yet, because this was actually 2 theta. See up here? We took the tan inverse, that is, we found the angle, but that was actually equal to 2 theta, which means that we actually need to divide both of these by 2, right? That is, we need to go theta is equal to 2 pi over 6, 5 pi over 6. Okay. Now, the question is this now all the solutions? Because now we're actually only going up to pi. We haven't gone up to all the way up to 2 pi. Okay. So we need to figure out what or how do we get the other solutions? Well, one thing that we can notice is that we just added an interval of pi at both of these, right? To go from here to here, we added an interval of pi. That is, we added a half rotation. And we notice that when we divide by 2, here to here, maybe I should do this in a different color, so you're not confused. From here to here, we are not adding an interval of pi anymore, we're plussing pi on 2. Agreed? So that means that if we can effectively generate some extra solutions, right? So we can generate some extra solutions by realizing that actually we can effectively double the amount of solutions that we got, because we know that if we halved them, we're actually going to get back to our original spot. So we can actually say, well, let's just go around another full time, and we can say that actually we get, I'll put these in a different color so that way we don't get confused. Let's do them in pink. So these ones aren't the solutions to this equation, but I'm writing them in pink to indicate or to show you that actually once we divide by 2, they will be solutions. So we're going to take 2 pi, this one, and we're just going to add a full rotation. So this is not just going to be 2 pi anymore. This is going to be plus 6 pi, so it's going to be 8 pi on 3. Okay, 8 pi on 3, and then it's going to be 5 pi on 3. We're adding another 6 pi, so 11 pi on 3. Okay, these are solutions. They're just originally outside the range, right? But because we're dividing by 2, these suddenly become in the range. 8 pi on 6 and 11 pi on 6. And suddenly these ones are now in the range and they will be legit, right? That is, if we multiply them by 2 and we take the 10 and then multiply by 3, we do get that value. So these are also solutions. Okay, so we would say this is the full 4 solutions that we get. Okay, and you'll notice that if you wanted a quick way to do that, you could have done what we did up here, like this bit, or you could have just realized that each of them were just adding pi on 2. Okay, and you can just keep doing that until you run out of range. Now, just a quick note on what your book says. Your book says, because 2 theta is double, when you take tan negative 1, okay, tan inverse, up here, instead of finding up to 2 pi, which is the original, find up to 4 pi to double. Okay, now if this is more intuitive, so if this is more intuitive, that's fine. But sometimes it is good to actually recognize what's going on here. That is, yes, you can just find up to 4 pi and then divide them by 2, but the idea is that this is exactly what was going on like in these pink ones, but we didn't really need to worry about doubling the range. We just kind of realized that if we took these first 2 solutions, that is this one and this one, they didn't take us all the way around, so we could keep adding the same interval, okay? And because it's symmetrical, we can keep adding the same interval and we will until the end of our range and we're still fine, okay? That interval of pi on 2, which was our original interval divided by 2. But if you find it easier just to double the range and do that, that's fine. All right, let's do the last one. Give the general solution and the first 2 positive and first 2 negative solutions of this thing. Now, this is an example of one, because there's so much going on in the equation, particularly inside the bracket, we're going to use the general solution, and then we're just going to vary our parameter, or k, to find the solutions. So basically, we just solve it algebraically for now. Root 2 sine of 3 theta minus pi on 5 equals 1. We're just going to isolate. So sine of 3 theta minus pi on 5 equals 1 over root 2. Okay? And now we take the sine inverse. 3 theta minus pi over 5 equals sine inverse 1 root 2. And then if I want to find that, I just draw an exact value triangle. And I recognize, actually, it's not this one. Because it's 1 over root 2, it's going to be this one. These angles are pi on 4, right? So I can say it's going to be pi on 4. And it is going to be pi on 4 because it's positive. Equals pi on 4, but because it's the general solution, we recognize that actually, for the general solution, we can take the angle of pi on 4 and we can just keep going around in 4 rotations. How do we represent those 4 rotations? Well, it's just 2 pi multiplied by k, where k is any integer, positive or negative. Okay, so k could be 1, k could be 3, k could be negative 7, and so on. It will always give us a sine value of 1 over root 2. And now we just simplify to get theta. It's just algebra from this point onwards. So let's simplify the right-hand side before we do anything else. If you need to pause at any point to get the algebra fine, that's okay. Do that as you need to. 8 pi k over 4. This is just fraction combinations. So 3 theta minus pi on 5 is equal to 8 pi k plus pi over 4. Okay? And now we just keep going. 3 theta equals this thing plus pi on 5. So 8 pi 4 plus pi. Okay. Plus pi on 5. Okay, and now we just got to get them on the same denominator. Yes, it's long, but it is just algebra at this point. So I'll do it fast, and if you need to pause to figure out how I did it, that's fine. Multiply top and bottom by 5, so I'm going to get 40 pi k plus 5 pi over 20 plus 4 pi over 20. So 3 theta is equal to 40 pi k, and then we combine the tops, plus 9 pi over 20. And then the last thing is to divide by 3. Theta equals 40 pi k plus 9 pi over, well, dividing by 3, so over 60. Whew. And I don't think that fraction can be simplified very nicely because 9 is only divisible by 3. All right, well, that was a lot. I'll just take a sec to write in all the steps. If you can skip forward a couple of seconds if you don't want to see these, but because there was a lot of algebra, I'll just write in the steps what happened. So we put them on the same denominator. Combine. Move pi on 5. Same denominator. Combine. And then we divide it by 3. Okay? All right. So now this is our general solution. This actually straight up is general solution. It's general because it gives us, well, it doesn't give us very much, except for everything, right? Like it tells us everything. We can just vary k to get any possible solution we like. So we wanted the first 2 positive and first 2 negative. So let's do the first 2 positives at k equals 0. So let's do this here. First 2 positive. And then you just basically need to change k to get the negatives and positives that you want. So the first 2 positives, let's say k equals 0, which gives us that theta is going to be equal to, well, 40 pi times 0 plus 9 pi over 60, which is equal to, well, the zeros cancel out. So 9 pi over 60, which is exactly equal to 3 pi over 10. No, 3 pi over 20. Okay, then we say k equals 1. It has to be integers, so we can't do fractions. Times 1 plus 9 pi over 60 is equal to 49 pi over 60, which you can't simplify. Okay. The first 2 negatives, so we'll say k equals negative 1. So theta is equal to 40 pi times negative 1 plus 9 pi over 60, which is, okay, negative 31 pi, I think, over 60, not able to be simplified. K equals negative 2. So see how I'm just varying k? Like at this point, it's just substitution. There's nothing too crazy, and we just trust the general solution will be fine. Over 60, which is equal to negative 80 plus 9 is negative 71 pi over 60. And that's it. 1, 2, 3, 4. And we're done. Yay. that's something that I don't think we could have just eyeballed off the unit circle. Okay, so that's a bit of a trickier question, but it's just really a lot of algebra. All right, so you've got 3 examples of solving equations. Go give some of your own a go, and yeah, see how you go. Have fun.